the idea with biased reference counting is the observation that most Python variables will only ever be accessed by a single thread. So the bias there is that you will probably not access this variable from outside the thread. Hi. Yeah. So I'm Tushar. I am one of the language engineers here at DeepSource. I mainly work with Python. I think I've been doing Python for 7-8 years now, I guess, something like that. Python has been changing at sort of an unprecedented rate in today's date. It's a bit crazy. It's fairly hard to keep up as well. Like if you're not aware of the developments, basically every part of Python has been swapped out with something new. Like, how many of you knew that Python had the fastest sorting algorithm of any language available? Okay. Do you know the name of that sorting algorithm? Yeah, TimSort, right? TimSort was named after this guy Tim Peters, who has been contributing to Python since 30-something years now. Well, TimSort is no longer the sorting algorithm in Python. That was replaced in 2021, I think. Late 21, an even faster algorithm has been put into Python. And yeah, that was 2 years ago. And everything from Python's tokenizer to the type system to the entire grammar to how the eval loop works, how the interpreter works, how it caches things. Basically, everything has changed in the past 2 to 3 years. And this is probably one of the biggest and the most disruptive changes that is about to come in the next couple years or so. And it has to do with the GIL or the GIL. I'm just going to call it GIL. You can decide whether it's the GIL or GIL between yourselves. But yeah, I'm going to call it GIL. And so this talk is about that. And I think it's something that all of you should be aware of, because it's going to change drastically how you think about writing Python code. So yeah, that's kind of what the talk is about. So first of all, what exactly is the GIL? So it stands for the Global Interpreter Lock. And it's somewhat of an implementation detail of Python. Now, the definition of it is a bit long-winded, so I'm just going to open the glossary page. Python has a really nice the glossary page, by the way. You should go ahead and read the entire thing if possible. But yeah, where were we? Yeah. So the global interpreter lock is the mechanism used by. Wait, where did it go? Come on. Yeah. The mechanism used by the C Python interpreter to assure that only one thread executes Python bytecode at a time. And it simplifies the C Python implementation by making the object model implicitly safe against concurrent access. That's kind of the textbook definition of the global interpreter lock. Well, in my own terms, it's basically a giant lock. And I guess we are going to get into what a lock is a bit later. But the important part that you should take away from that definition is that Python cannot multi-thread. But some of you might say, wait, Python has threads. Python has the threading module. It has, I think, 3 different modules to create threads right now. The problem is the threads don't really run at the same time. Only one of them runs sort of at a time. So it's kind of hard to understand just by words. So I think I'm just gonna do a tiny little demo for that. Yeah, okay, that works. Yeah, so we kind of have a dummy, a Fibonacci implementation that's really slow to kind of create a node for the program. And so what we are gonna do is we're gonna take the start time, and we are going to calculate the 36th Fibonacci number very, very slowly 8 times, and we're gonna see how long that takes. That's basically what the program is. So yeah, if we try to run that, it takes a while. That's gonna happen 8 times. All right. Yeah, did I mention Python is fairly slow? Yeah, 7, I believe, 8. Yeah, so that took 12.7 seconds. All right. Now we have a separate program. Wait. Yeah, let me open it up first. Yeah, so we have the concurrent version of the Fibonacci calculator. So we're going to create a thread pool with 8 threads, and we are going to spawn 8 separate threads that calculate that each calculate Fibonacci of 36. And let's take a look at how long that takes. Yeah, so the long and short of that is it's still going to be slow, but so the previous one took 12.7 seconds and this took 13.1 seconds. So it was actually a bit slower. But the important thing to note here is that the results kind of came together at the same time, and that's because the threads are actual threads. They're spawning the 8 separate threads on the machine. The problem is Python makes sure that only one of them can actually do the calculations at a time. So even though the workload has been spread between these 8 separate threads, it's kind of just a hodgepodge way of doing single threaded calculation. Yeah, so the Python has threads, but it doesn't have parallelism. It cannot do work parallelly with those threads. So what's the point of these threads then? Why would there be 3 different modules in Python to start threads and do all that? What's the point? Well, threads are still useful in Python, but they're only useful for IO bound operations. And the generic demo for that would be something like trying to download 10 files together. So say that you were doing that without spawning any threads. The problem here will be that waiting for every single network packet to arrive, the process will kind of be sleeping. It will be doing nothing. Say that this first part of sending a request, this takes say 100 microseconds, and then the thread sleeps for 800 microseconds, and then saving to disk also takes 100 microseconds. So so for one packet we took 1 millisecond of time, but 80% of that was just wasted, right? So if you were to spawn 4 different threads here and try to run them together, so what happens is this waiting time, it actually gives time for the other threads to start running. So because if one of the threads is sleeping, a separate thread can start the process of sending the request and saving to disk, and sending the request and saving to disk, and so on. So this is kind of the point of threads in Python, as it is right now. And from there, we should probably consider what was going on with with the whole locking thing. Why do we have this lock that prevents multiple threads to run at the same time? Every other language that you probably know of lets you run multiple threads at the same time and doesn't have this problem. Java lets you do it, Go lets you do it. Why can't Python? Well, the thing with the GIL is that it was a choice that Python made around 30 years ago. Now 30 years ago, multi-core processors were not really a popular thing. So that's an implementation detail that Python picked up. Now it's not necessary for Python to have a GIL. It's just that till now there had not been a better way to do it. without compromising single thread performance. Now, the thing that's important about the GIL is that it does not necessarily make Python slow. In fact, it probably makes Python faster for single thread applications. And for the longest time, Python was mainly used in single thread applications, which were scripts and many other similar programs, kind of like Bash. So that's kind of why there has been a global interpreter lock in Python. So not only does it keep the implementation of Python fairly simple, it also keeps it fairly fast, because all the data structures that are written in the C interpreter, like all the objects, all the dictionaries, all the lists, they don't have to worry about being thread safe and doing a bunch of locking and unlocking. So we basically trade that with having a single thread that does not have to worry about locking at all. So this was the case until 2016, where this old dude named the Larry Hastings came along, and he was like, hey, I don't like this. Every other language that I use can do free threading, where we don't have to worry about this big old lock that everyone just keeps talking about in Python. That hey, it's good, it makes single thread serve faster. So he went ahead and he announced that hey, I'm going to take the GIL out of Python, and he called the project the Gilectomy. The idea of that project was fairly simple: just replace this giant GIL with tiny locks, and every single a mutable operation that happens inside the interpreter in C, we replace that with a very small lock that can unlock. That's what every other language does. So why not do it in Python? So that's sort of the thing that he went ahead with. And turns out doing something like that is really slow. By the end of the project, Larry had realized that adding these bunch of locks instead of a single lock will it will speed up multi-thread processes for sure, but single thread Python performance it will be hurt by up to 60%. If we were to do the change that he did in the Gilectomy. So would you trade 60% of single thread performance just to be that whenever you're able to spawn many threads, you get maybe some more performance? I don't think that's the best choice. So that's why that project basically went nowhere. Yeah, that's until 2019, where this the smart little fellow called Sam Gross came along, and he was like, hey, so I think I can do this better. So there's a little detail here which is mentioned in this document. So he went ahead and wrote this giant document called Multithreaded Python without the GIL. And the nice part about this document was that it was way more thorough, way more thorough. But yeah, the sort of most important thing that's defined in this document is this the specific part. So there was a new technique which was sort of discovered in 2018 called biased reference counting. Now that's the difference, the main difference between the Gilectomy project and the current no GIL project, which came out of this Google Doc in 2019. If you were to notice, the Gilectomy it tried to leverage this thing called atomic reference counting to be able to deal with multiple threads still having to count the number of references that an object holds in Python. But the problem with atomics is that at the CPU level, it's still a fairly slow operation compared to just like adding a bunch of integers together. So this like a new idea of biased take reference counting said that it would solve that problem. And yeah, like there were a bunch of like different changes as well, such as the deferred reference counting and this like new malloc implementation, which was thread safe, called mimmalloc. Python's implementation of malloc, like it was not the thread safe at all, but not only was mimmalloc thread safe, but it was also faster. And yeah, similarly other like techniques like immortalization and like a few more that are like probably one too many to like directly name in the talk. Like you can go ahead and like read the entire document for that. Like it's quite a good document. I'll be honest. But yeah, the thing with like this doc was that like due to its like details and this new discovery of this thing called biased reference counting, turns out that you can do the exact same idea of taking this giant lock and turning it into tiny locks without harming single thread so performance by a lot. And in 2022, 3 years later, that kind of turned like into the current idea of PEP 703. And the thing with the PEP is that Sam had like a sort of a long game plan with his document, where from 2019 onwards, like he started the contributing to C Python some things that like don't depend on the entire like let's get rid of the GIL and like break everything. Like all the other good things that could be implemented, such as the better malloc, which also happened to be faster, and like the idea of immortalization and everything. Like these are all like already present in Python by the release of 3.11, and like he believed that that's the right time to actually go ahead and write a PEP, so that like we can sort of do a request for comments, where he can try to explain like how this project can now be viable. So let's actually take a look at what's going on here. Well, the thing with this PEP is that it's like even more longer than the Google Doc. But the basic idea here is that so Python does a bunch of reference counting to make sure that things that are no longer like a reference should be garbage collected. Like all that code will now be it will still go through, but in a much smarter way. I think I should try to go through the first implementation to make sure that we can explain this better. Yeah, so this was the 2016 version of the code, and let's see if I can try to explain this. Yeah, so the idea was that the parts that that would create this lock that would completely the freeze Python state and let only one thread run Python code at a time. That was going to be completely ignored. But things like dictionaries, what would happen is whenever say you try to delete an object from inside the dictionary, you will do a tiny little lock to make sure that any other thread cannot access that dictionary at that specific point while the deletion is happening. Now once the deletion happens, the lock is unlocked again. So basically, we take this giant lock and divide it into hundreds and hundreds of these tiny locks and unlocks. And PEP 703, like it explains that many of these changes can still be there while having these few differences. Let's see if I can find this. Yeah, the performance section. Yeah, right. So the changes like that were done with the biased reference counting method, like they would like decrease Python's single thread performance by like about 1.5%. Like that was the discovery that was made by Sam Gross in 2019. Similarly, by doing biased and deferred reference counting, like there would be about a 4% hit to single thread performance. And like a few other changes, to cause like a few more slowdowns. But the thing here is that that's like way lower than the 60% dip that had happened in 2016. Now, the PEP has been like mostly accepted at this point, which means that like in the next few years, these changes will be going into mainline Python, while the core maintainers, they have the option to try and revert this based on like how the results like turn out in the end. But like there is a pretty good chance that this like change will probably go through. But why? Like that's a good thing, right? Like sure, like some 1 to 5% dip is going to happen in Python's single thread performance, but we're going to see like a bunch of improvements, right? Now, like there are a few problems here that for the like next 2 to 3 years, you can expect that like there's going to be two separate versions of Python for a while, and that should remind you of the Python 2 to Python 3 change that happened, what, 10 years ago now? Some people are still using Python 2. Yeah. So, yeah, the problem there is that like a lot of people are like very skeptical about that. Python 2 to Python 3 change broke so many people's code, and like so much had to be rewritten that like there is still backlash so from that. Some people are like, hey, I don't care about like multi-thread code, like let my Python be fast as it is. And the third big problem is for library maintainers for packages that are like very important these days, like NumPy, like PyTorch, like TensorFlow, like Pandas, and like 90% of things that people like use Python for today. The problem here is that the CA, like the CA API that all these packages depend on, will have to be like different for Python without the GIL compared to Python with the GIL, which means that all these packages will have to maintain two versions of themselves as well, sort of. Well, that's kind of the theory of it, right? But I think that like this whole idea of there's a giant lock and then there are tiny locks and like that's why it's faster. I don't think that like that explains it like very well. So what I've done here is I've taken the code that was in the NoGIL branch created by Sam Gross, and I've installed that locally. So this a specific version that I have here is this the specific window will have the GIL, and this specific window will not have the GIL. Okay, so we're going to see sort of like what difference does it make for programs. So I think we should start again with the Fibonacci thing. Okay, so this program was the spawning 8 separate threads, and calculating the Fibonacci sequence 8 times. In the Python that still has the GIL, the threads are sort of working together, but not really. They're interleaved, but they're not parallel. So it takes about 12 seconds. But the Python version without the GIL with the same code runs in 2.81 seconds. Now that's 6-7 times faster. So you can sort of see that it basically scales with the number of cores that you have on the machine. Now this machine, I believe, has 8 separate cores. So the code can be up to 8 times faster by doing nothing. The code in both of them is the same. We're just spawning a thread, right? So that's basically where the value proposition for the GIL comes in. Now, we have a similar code, which does a thing that's fairly common with multi-threaded code, is trying to access global state. Now, the Fibonacci sequence, it's a cool demo, but no program really exists that does the entire computation purely, and does not interact with the libraries, the objects, and everything at all. So to sort of try to simulate what's going on there, we're going to have to do this little thing where we have this function which takes the global variable and it tries to increment it a million times. Okay, and we do the same thing. We start 8 threads. So we take the the global variable and we increment it a million times, but do the same thing 8 times. So the final value here should be, it should be 8 million. So let's see how that goes here. So that took 1.57 seconds on Python with the GIL. And so now, what's happening here? It took 7.67 seconds on Python without the GIL. So it's kind of flipped, isn't it? Right? It's something like 5 to 6 times the slower. So what exactly happened here? Well, the thing that happened here is lock contention, and that's the one thing that Python Python developers don't want to think about. So the thing that I glossed over here was this lock. Let's actually go ahead and comment out the lock part, and let's see what that does to the Python without the GIL. Though it got way faster, it ran in 0.37 seconds, and but without the GIL, hey, that is much faster, 1.6 seconds. It's still slower than the Python with the GIL, but it's way faster, right? But hey, the answer is all messed up. See, that's the thing with locks. Once the global interpreter lock has been taken out of Python, it's now the responsibility of the Python developers to make sure that whenever multiple threads try to access the same object, that object is locked. That's why we have to do deal with locks and lock contention and all of that jazz. Now, single-threaded Python did not have to worry about any of this at all. In fact, even with the commented out code, it didn't really matter, because there were 8 threads, but only one of the threads was able to run x plus equal to 1 at a time. So all the 8 million times this happened separately, but this started clashing while it ran on multiple threads without the GIL. So that's kinda the entire point of like GIL versus no GIL. Like it's not just sunshine and rainbows. Okay, let's actually look at a couple more examples. So the third example I have right here, like we'll try to explain why the Python, like even without the lock, the multi-threaded Python is still slower than the single-threaded Python. So the thing with threads and lock contention right now is it can be simulated in the Python with the GIL with multiprocessing. Now the difference between multi-threading and multiprocessing is that since multiprocessing spawns a completely different process that has a completely different GIL. So your your Python code, it can actually run parallelly to each other. But the problem with that arrives when you try to run it. So that exact same code trying to calculate the 8 million number. It took 11.47 seconds, and weirdly the value of x at the end is 0. The code is exactly the same. The only thing that has changed is that we went from a thread pool to a process pool. Now what exactly happened here is that multiple processes cannot just talk to each other. When you spawn a child process, all the variables that exist in the file, everything from this function to to the value in the x to all the imports that you have up top, they will be copied to the new process. So while the child process is doing all the locking and incrementing and locking and incrementing, that's happening with the version of x that exists for that child process. So these 8 child processes, they calculated x to a million just fine, but they never got added up to the x that was in the main process. So that's the that's the main problem that existed with multiprocessing, where a process multiprocessing is cool, it lets you run Python parallelly, but being able to transfer data between each other is a completely different hassle that I don't want to get into. And the thing with Python without the GIL is that when you try to spawn threads, you get the exact same problem that you get in the current Python with multiple processes. Now you can do multiple things at the same time, but you have to worry about things like locking and convention and everything. It will be a bit faster because the threads are faster to start up than take an entire new process with the with a new GIL, but the problems still remain. Let's look at program number 4 here, where we simply run the famous linter flake it with 8 different threads on the entirety of the CPython repository. Let's run that on Python with the GIL first. So so it's going to split the repo into 8 different sets of files. Then it's going to process all of them together. And it looks like with the 8 different threads, it took around 9.61 seconds. Now the thing here is that there's no a global value access. Even the imports are happening in here, and we're not accessing any value that was outside the function. So this is kind of a pure function, right? This function should run much faster than the no GIL branch. So let's take a look at that. Well, it did run faster from 9.61 seconds to 4.23 seconds, but the speed up is not as high as you would have maybe expected. And the thing here is that the libraries that we use are not currently designed to be completely compatible with the free threading. Now, the flakehead the currently creates like a bunch of these global objects, like the application object, and then the checker object that like stores all the results and everything. And when like multiple threads are trying to run like on multiple files at the same time, they all have to write to these same objects. So that creates the same contention that we talked about. So like even though like the code got faster, which is like a good thing, like it's not necessary that like everything will just like magically get faster if you try to write pure Python code. Like especially with like most code bases, like Flakeit is like sort of a rare example where it's written like the fairly well. Like if you like were to try to run like just in a regular old program, like between the GIL and the no GIL version, you will probably not find much of a speed boost at all. You'll have to make significant amount of changes to these programs to make sure that they can be good with the free threading. And yeah, that's sort of the demo that I had for you. So yeah, let's like talk about like the future. That hey, yeah, GIL is going away. That means that we have to start worrying about a bunch of things, but we also get free performance sometimes. But yeah, so what do we do about it? Yeah, so the PEP has not been accepted yet, but it will be. Like the current explanation by the steering council is that Sam Gross has done like really good work, but a lot of work has still to be done. So like it will be a while before this change gets like accepted into mainline C Python. Probably like it will end up in C Python by release 3.14, which is the like the Pi release. But like in between that time, it's probably like a really good idea to go ahead and try like your own programs and like so be a bit more aware of what this change is going to mean for like for your code bases and for your libraries and so on. Now, the big thing is that the Python Steering Council and like the set of C Python code is, like, that exists, they have like learned a fair bit from the change that they did in Python 2 to Python 3, and they like are like very hopeful that the way that they implement this new change will like try not to affect like most Python developers as possible. But the most important thing there is they require feedback. So if like you're a library maintainer, make sure to test it like on the GIL, the disabled version of Python as soon as it comes up. Like it will probably be out in somewhere between 6 months and 1 year from now. So like if you maintain like a Python application or a Python library, make sure to test it on that. And if you find that there's like a major like a degradation in performance, or some things that should be working like are not working at all, make sure to report that, because like if you don't speak up, the coders and the maintainers have like no idea what decision to make. So yeah, that's like a kind of the talk. Like a quick recap. Python is going to get like a true multi-threading, but like it's not as black and white as that, as you saw. Now it can possibly like to speed up your programs by default, but you should not rely on that fact. But you can start parallelizing a lot of the things in your code base to speed it up going forward. And yeah, it's going to be like way more simpler than multiprocessing. I would assume that some of you have tried to make your code faster by using multiprocessing. Like it's a very painful process. But yeah, with threading, like it will be a bit less painful. So yeah, and like if you have a library, like you should probably start making it thread safe with locks and like stuff like that, because people that were writing Python code before and like that were using your library, that kept working like even without like any the worries about like a concurrency control and locks and like maintaining the correct state. But like that's going to change very soon. Like even like regular people like running Python code will be like using a bunch of threads, because like it will give give them a bunch of free performance. So like if you want to make sure that your library still keeps working in that condition, you should start looking into thread safety as soon as possible. And yeah, that's basically everything I have. I have a blog where I talk about Python, and like if you want to talk with me about Python, you can talk to me on the app that used to be called Twitter. And yeah, like that's it. Thanks. So any questions? The question here was that the Fibonacci code that like it was about, yeah, like it was about 8 times faster by using 8 threads. So why not use 12 threads and make it 12 times faster, right? So yeah, let's actually try that, because why not? That's going to take a long time. It's going to take like 20 seconds on the Python with the GIL. Yeah, come on. So, okay, 19 seconds. Yep, fairly spot on. So if you do the same on the Python without the GIL, yeah, it's 4.26. So what does that come out to? Sorry, my bad. It's about 4.5 times faster. It's even slower. Oh no. Yeah, well, the limitation is that like you only have 8 cores. So like only 8 of them like will run parallelly. So the last 4 are actually going to run while like 4 cores are sleeping. So it's going to be even slower. So yeah. Well, the best thing that you can do is start using your library with multiple threads, and then like you'll spot a bunch of crashes and like a bunch of inconsistent states and things like that. And like with